Okay, good afternoon. Can everyone hear me? Can everyone mic? Yes, but okay, one person can hear the mic, that's good. So my name's Joe Greenwood, as I said, so I'll do a brief intro about me and then talk more about why you're here, which is the collision avoidance bit. So what do? I'm an aerospace engineering student, or was an aerospace engineering student until last Friday, at the University of Bristol, which does aerospace. See the helicopter, it's aerospace. But I'm also a sponsored undergraduate in the Royal Navy, going as a pilot, flying F-35s, a Joint Strike Fighter. And the question that you've probably all got on your minds right now is, so I will be flying Joint Strike Fighter, but at the moment I just run up and down hills with large weights, which isn't exactly great. But the question you have is, why am I here? So why am I here at an InfoSec conference talking to you about InfoSec things? The reason is, for the past 4 years, I've done the Cybersecurity Challenge UK, and out of that I got a load of CREST qualifications and other courses, and that allowed me to go away and do an internship with BAE Systems Detica, now Applied Intelligence, so some of you guys in the room at the moment. And now, at the moment, I do consulting with Forearmed, so I think Mark's in here somewhere. And I do pen testing, red teaming, and sort of security consultancy on that side. So essentially, I took the hacking side, because that's what hackers look like, right? And the Joint Strike Fighter side, and the pilot side, and the avionics side. And that gave me a pretty epic master's project, because this is for my university course. We get to propose our own master's project, so I proposed something that took InfoSec and planes, which is always a good start. And you can tell it's a good master's project when your risk assessment includes accidentally crashing aircraft. So that one was quite interesting to get past the university risk assessment people. But yeah, that was quite entertaining. They didn't notice until I pointed it out, and then they were like, ooh, we should probably think about that. But anyway. Okay, so what we're going to look at is what is this magic ADSB thing that I'm going to talk about? Where does that come in? What can we do to it? I mentioned collision avoidance, so there's a system called TCAS, or the Traffic Collision Avoidance System, which does what it says on the tin. And then overview of all of the complex security mechanisms involved in those two. And then I'm going to explain and demonstrate the attack that I've proposed for it. And I'll have some live demos if we give an offering to the demo god. We'll see how that goes down. And then, shock horror, I have some defenses. So they're not great defenses. I'm going to caveat that. There's not much you can do with legacy protocols in general, but I'll sort of explain some of the prototypes and some of the ways you can go through that. And then at the end, we should have some time for questions, which should be good. Okay, so the ADSB stands for Automated Dependent Surveillance Broadcast System. Automated, and the pilot doesn't have to keep clicking transmit. So dependent, and it's dependent on other sort of systems, so GPS and altitude and all that sort of stuff. And then surveillance, because the ground traffic control can use it to surveil aircraft. And then the broadcast bit is self-evident because it transmits. So essentially, you have your GPS satellite up here, and your aircraft gets its data, its position, its speed, its velocity, its state, essentially, from that GPS constellation. Then that aircraft formulates a message and then transmits that over 1090 megahertz with a special squitter format to ground stations. So they're beaconing out broadly once or twice a second their position and their state. And then the ground stations can use all this data to use air traffic control data because it's quicker than radar. So radar actually is quite slow to do a complete cycle, so it's useful for them to have better situational awareness of where the aircraft are. That's that side. That is called ADSB out. So that's the aircraft broadcasting out its position. There's another system called ADSB in, where other aircraft listen for the ADSB transmissions. So they're taking in the ADSB data and using that to work out where other aircraft are around them. And that's the bit that we're going to be looking at. So some interesting facts about ADSB. It's mandatory in Australia at the moment. It will be mandatory in Europe for 2017, and it will be mandatory in the US in 2020. And that's part of the US's Next Gen program. And hopefully, by the end of this talk, you'll realize why I laugh when they say it's next generation. So we'll get to that bit. And the key aim is it aims to replace primary surveillance radar entirely. So just have this. So bear that in mind when we get to the end of the talk. So the collision avoidance bit that everyone was interested in, the Traffic Collision Avoidance System, so TCAS, aims, funnily enough, to stop aircraft colliding, which is always a good thing, we'd hope. So this was brought in 1978 because an airliner, so I think it was an A320, impacted with a light aircraft over San Diego. And at that point, for some reason, it was that collision, rather than all the other air traffic collisions, that they decided, you know what, we should do something about this. So they invented this system where TCAS takes in data, and then it works out whether there's going to be a collision with another aircraft based on that data. If the aircraft, so this is our intruder aircraft, is within 40 seconds, it gives the pilot a warning, so a traffic advisory, or a TA. And that basically goes off in the cockpit, you get display, it goes traffic, traffic. And that tells the pilot to begin looking visually to see if he can see the aircraft. Useful. Then, however, if the aircraft comes within 25 seconds of collision, you get a resolution advisory, or an RA. And that's normally given with an order, so it would be climb or climb now. And the idea is that both aircraft will negotiate which one goes up and which one goes down, which is a good thing, because if you both pull up, you still crash, which isn't great. And there's some protocols behind how all of this works on the back end. This is the actual display the pilot gets. So you can see here, these are two non-threatening aircraft, just displayed for traffic information. The orange circle is the TCAS T8, the traffic advisory, and the red square is the resolution advisory, the RA. So remember these symbols for later when we have a look at those exact displays. So the overview, so like I said, there's multiple data sources, so there's active modes, and that uses the mode S transponders. So they talk to each other and try to work out the range and the bearing and that sort of stuff. But they're also bringing in using ADS-B in to give traffic data. And the exact extent to which that works isn't entirely certain. So my project was trying to look at whether you could use that to do something interesting. So some of you will have already spotted the problem with ADS-B in and TCAS, but we'll get onto that later. So again, some interesting facts about TCAS, just to bear in mind for the rest of the talk. TCAS has a higher priority than air traffic control. So if you get a TCAS RA, you ignore air traffic control while you're responding to that RA. That's an interesting thing to quote. Pilots are mandated to respond to it within 2.5 seconds. There's not an amazing amount of thought time in this. You see the red blip, you do what the red blip says, essentially. And the last thing, on modern Airbus aircraft, autopilot is slave to TCAS. So as soon as that thing goes climb, the aircraft will be climbing. So again, those are 3 things to bear in mind for the rest of this talk. So the security. This is the part of every conference presentation where I sit here and I talk through the labyrinthine complexity of the security, how I used wit and guile to bypass it all and get an exploit at the end. But Morpheus has something to say about this. So actually, there is no security on ADS-B whatsoever. There's nothing. There's no encryption, there's no authentication, there's no integrity checking the message okay. It just blindly assumes that anyone who's transmitting is an aircraft, and that they don't actually have to be wherever they can. So obviously, as the most interesting man in the world says, if you want to get rid of radar, you obviously make sure that your protocol allows anyone to be wherever they are, or wherever they want to be, rather, for this. So there isn't any security. And my project supervisor, initially, he's a crypto expert at Bristol, he was like, no, there must be some security. There must be something on there. Someone will have put something. And it was only when I showed him this is Flight Radar 24, where you can view all of the aircraft transmitting ADS-B. So this is essentially an ADS-B in receiver for all of the ADS-B that the aircraft are transmitting. And as you can see, you can pretty much get all of them. So there's already, ignoring everything else, there's a surveillance risk with ADS-B that anyone can tell where an aircraft is because it's required by law, or will be required by law, to transmit its location. So if you, for instance, wanted to sit at the end of a runway and work out exactly where an aircraft was going to be, and you happen to have a surface-to-air missile, then who knows, maybe you could do something interesting with that. So there's a whole issue to that I'm not really going to cover, but I'm sure you can see where the issue's going. So the exploit pathway, for want of a better word, for what my project intended to do, was we'd have an attacker system, and we'd generate these ADS-B messages to try and pretend to be an aircraft in front of another aircraft. And at that point, hopefully, TCAS should go mental. So we generate messages for a software-defined radio, and then we transmit these over the air. The ADS-B receiver then decodes these messages. It doesn't do any checking on them, because it just decodes messages, that's what it does. It then passes them to the TCAS system, and then depending on what the TCAS system will do, we'd like it, or rather we wouldn't like it, to alert the pilot with a resolution advisory and tell him to climb. So this attack in general. So obviously, avionics hardware is quite expensive. And I don't know if you've seen the state of academic funding at the moment, but it's not great. And it certainly doesn't stretch to buying an aircraft. So when I went to my supervisor and said, can I buy an entire ADS-B and TCAS system? He said no, quite flatly. He did, however, have a load of software-defined radios floating around, so we got to use those. So I put together an ADS-B and TCAS testbed using software-defined radios and GNU radio. So the idea is we listen on 1090 megahertz, or whatever we're listening on, and then we have an RTL SDR dongle, which are really cheap, really easy to get hold of, well within the academic budget. And then we've put that into GNU radio, so there's GR Air Mode S. It's something that Nick Foster made. I think it's called Bistromath, his handle, which is a Mode S receiver, but done in software-defined radio, which is quite handy. That then decodes the ADSB messages and then sends it to a flight gear simulator, essentially. So flight gear is an open source simulator that happens to have a TCAS receiver in it that is compliant with TCAS version 2, TCAS 2 version 7.0, sorry, which is the last but one version of TCAS, which is quite handy for me when I'm trying to make it as close to reality as possible. So then we have our decoded packets, they go to flight gear, and then they trigger something, or they should trigger something. So I did this with a real aircraft. So this is listening above my house, and this is an EasyJet flight that was flying over me at the time that caused a TCAS alert to come up on my flight simulator. So from a flight simulator perspective, that's quite cool, but that's not really why we're here. We're here for more the InfoSec side of it. So we need to generate these messages somehow. So the question you're asking is, what does an ADSB message look like? You start off with what's called the DF bit, or the downlink field, and that's because ADSB is a subset of Mode S. So there's loads of different types of Mode S message of different types, and this bit tells it what type it is. And for ADSB, that's OX17, or OX17, and that's ADSB messages. So all ADSB messages will have OX17 in here. Then you don't need to worry about that. And then you have what's called the ICAO address. So ICAO is the International Civil Aviation Organization, or authority, and they manage aviation across the world, essentially. So every aircraft that gets built above a certain size gets given a unique identifier. So if any of you have been on ships, you have the maritime number, registration number for your ship, and you have the ICAO address for your aircraft, which is your unique ID. Obviously, you want to transmit that with your ADSB messages so that you can tie up your aircraft to your ID and you don't get anything like that. Then the next 56 bits, so this is 24 bits, by the way, so it's not a large amount of space. 56 bits here are ADSB data of various forms, and then we have a really complex CRC32 checksum at the end, just to make sure everything's all right. So actually, I did say there was no integrity. I lied slightly, because there is a CRC parity check, but I wouldn't really call that proper integrity, and it doesn't actually validate who you are, but it makes sure that it gets there in one piece. Okay, so there's three main types of message, so subsets within this ADSB data that we need to send. We essentially need to send our position, pretend to send our position, our velocity, and we also send an identification packet. And these are all identified by the register that they're stored in memory in the ADSB receiver, and that's called the BDS registers. So position messages are BDS05 messages. So that's the sort of the way we determine where those messages go. So BDS05 messages look like this. So we have our altitude in those bits, and then we have our latitude and longitude encoded in something called compact position reporting. And that's a way of compressing the latitude and longitude into a very, very small amount of space by using longitude zones. And you could do a whole hour presentation on just doing CPR, longitude, and latitude, but you probably want to kill yourself at the end. It's not very interesting. The thing to take away, though, is that you get very, very compressed, but you need two messages to narrow it down to which side of the Earth you're on, essentially. So if you have just one BDS05 message, you can tell whether you're in one of two places on the Earth, and then you use the second BDS05 message to narrow it down to exactly where you are, which is quite handy. So we have two of these messages. That gives us our position, so our altitude, latitude, and longitude. We then have something called an ident packet, or identification, which is BDS08. And so the ICAO address I mentioned before isn't really very human readable. It's hexadecimal numbers and letters, basically. So for air traffic control, they'd like to have a good human readable call sign that they can assign to it. And that's what this packet gives you. So the first thing it has is the aircraft category. That hasn't come out very well, has it? And that tells air traffic control what type of aircraft you are. So that could be anything from a light aircraft to a heavy aircraft. You can be a parachutist in the spec, apparently. Why a parachutist would carry an ADSB transmitter, I've got no idea, but you can do it in the spec. And then all of the rest of the bits are the characters in the call sign. So earlier on, we had that EasyJet flight. That was Echo Zulu Yankee 61 Golf Romeo. So that's these 8 characters here, which are your call sign. So when you look up what your flight tail number will be, it'll be that call sign there, not the account address. So we've got our ident packet, we have our position packets, and now we have our velocity. And this will take you back to GCSE maths, essentially. The velocity is given in east-west velocity and north-south velocity. So obviously, to get your heading and your speed, you just do trigonometry on those. So it's good old-fashioned maths. So then, with all of that, we have our velocity, our position, and our ident packets. An interesting thing to note, actually, about these velocity packets is you get to specify what your uncertainty is about your velocity. So obviously, all of the fake aircraft we're creating are 100% certain about how fast they're going. They're not uncertain in any way, shape, or form. So obviously, then, the easiest way to make something trivial is to make a Python library for it. So I wrote up a Python library called libadsb that you give it some data, and it gives you out a nice ADSB message here. So for this one, the account address is beef11, because you can do that with hex, why not? But it makes it really, really easy to generate lots and lots of different messages, which is what we need to do later. So we have our messages generated, now we need to transmit them. So I used a HackRF, because that's what the university had lying around, as you do. We didn't have the budget for any of the ETIS radios, which ideally we'd have used, but we had one of those. So, and then using GNU Radio, you create blocks to your diagram. So this block diagram is lifted nearly exactly from some research done by the US Air Force over at AFIT, so the Air Force Institute of Technology, in 2008, where they did some work on false traffic injection of ADSB. And essentially, you have your binary message encoded in the form that you want to transmit it in. You unpack it, and then you just transmit it. It's very, very simple, very easy to do. However, it turned out that it didn't actually work. And quite why it didn't work, I don't actually have any idea why it didn't work. So this is the transmitting side. So this is the pulses that I'm transmitting. And this is what came out on the other end on the receiver. So as you can notice, they're not actually the same at all. And this didn't trigger GR air modes to do anything. So that didn't work, and I spent a long, long time trying to get it to work, but it didn't work. The interesting thing to note is I wasn't transmitting on 1090 megahertz, because obviously that's illegal. I was transmitting on 433 megahertz, which is the International Scientific and Medical Band, which is free for anyone to transmit on. So I was doing it at a lower frequency. And one of the possible reasons this didn't work is that there's a lot more noise on 433 megahertz than there is at 1090, because hopefully, there's only aircraft on 1090 megahertz, whereas every man and his dog is transmitting on 433. The other potential issue is because I wasn't at 1090 megahertz, my encoding of the actual message wouldn't possibly be right, so the sample rates might be mismatched between the RTL SDR and the HackRF. And then there's just the issue that the RTL SDR, it cost £5 off eBay, I think. It's not exactly high-end equipment, so it might be that it's just not doing the precision I need. So this could be fixed if I did actually transmit at 1090 megahertz, but obviously I need a Faraday cage or something to do that in. However, there's a good reason why I didn't, is that if you can't do something here, there's probably someone in China who's done it in legally dubious circumstances. So there's this gentleman over in China who's done exactly what I was trying to do, but on 1090 megahertz. So that's interesting. See if I can get that to play. So he's got his HackRF wired up with his laptop. He's transmitting the messages using the identical GNU radio blocks that I had. Here's his software SDR, RTL SDR even. And then you can see the aircraft just at the bottom there going sideways in a square shape. And as someone who's done 4 years of fluid dynamics, that's not normally how aircraft fly. I'm sure maybe you picked that up. But yeah, so here's him moving his aircraft around quite happily. And if there was another aircraft there, they probably got quite confused by this aircraft moving around in a square pattern. But maybe they don't have laws against that in China, I don't know. But there, so he's done it. So it's not that that can't be done, it's how that links to the rest of it. So that wasn't really the important bit of the project, because people have been injecting ADSB for quite some time. And if we could do that, we have a YouTube video of someone doing it, so we can show that that's an issue. So at this point, it was time to simulate it all, so we just skipped ahead doing the RF bit and just cut that down to software. Because that's what you do in academia, right? You simulate it all. So at this point, GNU Radio has quite an interesting feature, or GR Air Mode, sorry, has an interesting feature where you can specify multiple other radios and send messages into a central server over ZeroMQ sockets. So essentially, you could have a farm of distributed sensors and then bring in all of the ADSB data into one. But that also means it's quite useful for us, because we can write a little Python script that injects messages into the message queue to be decoded. So it quite happily bypasses all of the RF injection stuff, and we get to go straight into here. And that's probably a valid assumption to make, because it's exactly the same message, it's just not getting transmitted over RF. So win for simulation there. So obviously, if you want to be a hacker, you have to write something with green text, because that's how it works. So we had a console program, or I wrote a console program, that allows you to specify all the different things, so the call sign you want, the latitude, longitude, speed, all this stuff, and then obviously have help. And then this generates it all in the background, it transmits it into the GR air modes thing, and then it gets decoded. So this gives us a nice front-end interface that we can then type in, change the latitude to this, and then we can mess around with putting aircraft in front of them and moving them dynamically, which is quite useful. Did it work? Yeah, it worked in my simulator. So this is the aircraft UOB hack, sitting there in front of my aircraft in quite a threatening position, injected into it. And that is the TCAS display with a resolution advisory shown. So at this point, TCAS was saying climb, climb, or descend, I can't remember which. And at that point, in real life, if this all worked as expected, then the pilot would probably be having a small shit and pulling up. But if we can do one, we can do loads of aircraft, right? So, like I said, because you can pretend to be an aircraft, there's nothing stopping one aircraft pretending to be hundreds of aircraft in lots of different locations. So I think this is 30 aircraft, all clustered around. And at this point, it's quite interesting, actually. My TCAS receiver didn't know what to do at that point, if there's aircraft above and below it. So every half a second, it would change between telling you to climb and descend. So you get climb, descend, descend, climb, descend now, and all this sort of stuff going on. So if you were a pilot in that position, you'd probably know something wasn't right, because you couldn't see all of those aircraft out the window. But by law, you'd be mandated to do something. What that thing was, I don't think anyone could probably guess, and that'd be up to the lawyers to decide. But it's not a great position to be in if you imagine you're on the approach at Heathrow and that's what your display looks like. Okay, so now we pray to the demo gods and we see if it actually works on screen. So we'll have a go at this. So while that's starting up, we've got this is our injection program. So our console. And then over here is our GR air modes transmitter. So that's going to decode the messages. And then the multiplayer server for flight gear is running on this Kali Linux box as well. And then our front end, whenever it loads, decides to load, connects to that multiplayer server and then gets all the data out of that. But it's loading the scenery, apparently, which is obviously something we're interested in. Yeah. So that's going well. Somewhere in the States, apparently. For reference, this is not how I fly planes. It'll sort itself out. I think the autopilot has an interesting opinion about where we're going. Okay, so eventually it's going to turn around back to the course I originally told it to go on. But we're just going to put this up here. So over here in our console program, where it's gone, over here. So if I go help, we get a list of commands, which is very helpful, about all the different things we can set. And then if I go shot options, we get a nice little picture of all of the different things that we can set for the different places. So that's really small, isn't it? So we're going to set the longitude to -2.9. And these are just some pre-worked out values that should possibly put it in vaguely the right place to trigger an advisory. But it depends on where the aircraft decides to put itself. Okay, so oh no, I forgot to set them. There you go. So over here in our TCAS receiver, we have the, for some reason it's not saying climb, but it's a pretty buggy simulator anyway. But there's our resolution advisory showing up on the screen. So because I can just arbitrarily do whatever I want to it, I'm going to move that back. So we're going to set the longitude to -3.1. And over here, you should be able to see it magically disappeared, and now it reappeared again, because it's just further away in front. And like I said, obviously, if we can do one, we can do multiple of them. So we're going to set the path to swarm, which just randomly generates something around a point. And let's put 10 aircraft in. So let's see if we can do this at the same time for maximum effect. So there's our 1 aircraft, and now that's become 10 aircraft, all with traffic advisories. And then, like I said, if it's within 40 seconds, you get a TA, and then those will slowly turn into red dots. There we go. So now there's a small swarm of unidentified aircraft coming straight towards you, all causing resolution advisories, which isn't a great position for a pilot to be in. So amazingly, that worked. Right. Okay, so that's the demo of that side. So obviously, as InfoSec professionals, we do all this sort of attacking stuff and we demonstrate the exploits, but ideally, we'd like to have some defenses against that particular stuff as well. So the second half of my project, once I got all of that done, was trying to implement some defenses to stop people being able to arbitrarily inject packets into ADSB. So trying to put the confidentiality, integrity, and the sort of encryption on it that you'd expect to see in most safety-critical systems, ideally. It is an interesting trope, as an aside, that the systems that we rely on for be the most secure and the most safety critical, ironically have the least security. If you look at your iPhone, for instance, and the security on that, compared to the security on most SCADA systems and on this, I don't understand who decided to put the money in which particular location there, but that's another issue entirely. So the first thing we try to look at is symmetric encryption. So if both parties have a secret key and they share the secret key, and then encrypt their data with that and decrypt it at the other end, ideally no one should be able to decrypt that traffic to work out where the aircraft is, or make false traffic by injecting data. So I used AES and Blowfish and tried all those different combinations out. But there's some problems. Because it's a really, really small amount of space, it's smaller than the block size for most block ciphers, so you end up having to use a stream cipher, which isn't ideal. But you can use a deterministic nonce or initialization vector, so that's not really an issue. Interestingly, about 6 years ago, someone wrote a military paper about using this sort of symmetric encryption for a military ADSB system, where you have symmetric encryption on it, and then you detect whether the plaintext is meaningful. Because obviously, if you don't have the secret encryption key, you can still make a message and it will get decrypted, but it will be garbage. So the question is, can you work out if that's garbage, or is your ADSB receiver just going to go, yep, there's an aircraft there, and just blindly accept it? So at this point, you have to put some sort of heuristics in to try and work out, does that make any sense? Is that meaningful plaintext? And then do something based on that. Whether the actual military system works like that, I don't know, because they don't publish it, but that's an interesting idea put forward, to sort of provide some authentication via just a single secret key and stream ciphers. So an interesting question for us as aviation people is, does that slow it down? So if you put encryption on it, it's going to slow down, but by how much? So compared to the solid lines are just normal ADSB, and then the dotted lines on the top are encrypted with AES CFB. There actually wasn't that much of an increase in time. So it's about 150, 120% extra time over just normal plain ADSB. And the reason that matters, if I put that in context, is if you're an airliner traveling at sort of 900 kilometers an hour, if you have a delay of 1 second, that equals 265 meters that you've closed between your target. So if your thing takes 1 second longer to decode something, that means that you're a quarter of a kilometer closer to hitting the other plane, which isn't great. So obviously there's some issues with that in that if one person finds out the key that you don't want to find out the key, you then have to change the encryption key on every single aircraft in the world, which is a lot of aircraft. So Airbus has 15,372 aircraft on order alone at the moment. So if you then had to change all of that aircraft, all the keys on the aircraft that you haven't built yet, because someone found out the key, or probably someone at this conference found out the one secret key to your device, and that's not going to work. In the military, it sort of works because you've got a smaller number of aircraft, so you can just go on and plug a USB stick into each one and do that. But that doesn't really, it's not really distributed enough for a civil aviation solution. The rest of the solutions I used, because of we have this really, really small amount of data, there's no extra room to put stuff on. It's not like you can suddenly add another 128 bytes on the end. There's just nowhere for it to go. So you have to have a second channel to put data inside. So luckily, there's a sort of workaround for that in that, like I said, ADSB is type 17. There are type 24, type 24 messages that are defined where you put 24 at the beginning, and then you can have 80 bits of arbitrary data, and then you can smush 8 of those together to get 1,620 bits, I think, of data in a block. So you transmit 8 of these messages in a block, and you get that large amount of data out at the end. So I defined a sort of custom protocol based on that, where you tie it in with the ICAO address of the aircraft you're transmitting. You have your data block of generic data, whatever it might be. And then at the end, rather than doing a parity check of this data, you put the CRC of the message that you're referring to. So say you want to sign another ADSB message, you take the CRC of that message and put it at the end, and then you can reference all of this to that one particular message. So there's 2 schemes that I developed to use this. The first of these is an authenticated encryption and decryption. So like I said with symmetric, you don't get authentication automatically. You have to sort of put the heuristics on top of it to make sure that that works. But if you use an AAD scheme, then you get authentication. So you can tell using this tag whether the person actually had the right key to make the message. So essentially, you have your ADSB message at the top, and you put it into the encryptor with your secret key, which is symmetric again, unfortunately, and a nonce value. And out of that, you get an encrypted ADSB message, so that's stream ciphered encrypted, and an authentication tag, which is essentially an MD5 hash, that sort of length. And then you can split that between 3 type 24 messages and then transmit those. So you get one of ADSB message and then 3 other messages for each one. And then at the other end, you receive all of those, and then you put them into a message queue, and once all 4 of those messages are received, you can then put them into a decoder with the secret key and the deterministic nonce that you can work out, and then you get a decrypted, validated ADSB message. So win. However, it's still symmetric, so you need the key on both sides. The other disadvantage is, for every 1 ADSB message, you need 3 type 24 messages to make that work. Now, I remember when I said the smallest number of messages you could have was 2 BDS05, 1 ident packet, and 1 velocity packet. That means you need 12 messages then, just to transmit those 4 messages. So you're reducing the bandwidth of the ADSB system by 75%, pretty much. And at the moment, ADSB is operating at nearly max capacity around Heathrow and places like Los Angeles. So reducing it by 75%. If you turn around to Heathrow and said, sorry, you can have security, but you'll have to fly a quarter of the aircraft that you're flying at the moment. They're probably not going to take you up on that. So that's a massive downside for this. An alternative to that is if you just use the hash message authentication code, so like an MD5 HMAC, you'd get the 3 type 24 messages, but you wouldn't get the encryption. And that's a plus and a negative. So the plus is that you wouldn't have to change any of the ADSB hardware. So that would be an enormous cost reduction because you're just sending ADSB messages. But the downside is you wouldn't get the encryption. So you still have the surveillance risk, even though you've validated all of those original messages. So there's ups and downs for all of that sort of stuff. The second side of it is I looked at some research done by some guys on vehicle automotive, so putting authorization and signing on the CAN bus. And they used elliptic curve cryptography to do signatures because they're very, very small signatures essentially get out at the end. So I use this NIST 192P curve. And again, so the idea is you have your set of 4 messages that you need to send. That's your block of state data, basically. You take all of the data from that, and then you then sign it with an aircraft private key that you sort of burn into the firmware of the receiver. Then you get a 384-bit signature. Now, in the grand scheme of computing, that's tiny, right? So that's nothing. You could send that over thing. However, in this protocol, you need 7 type 24 messages to send that 384-bit signature. So you can see at the moment working with these sort of legacy protocols is sort of very tiresome when you're like, how do I fit all of this into the smallest amount of space possible? Because there's nowhere left for it to grow. So at the other end, you get your 4 ADSB messages and your 7 type 24 messages. And then you look up in a public key database what the aircraft public key that it's saying it is via the ICAO address. And then you get the payloads and you reconstruct the signature by putting all type 24 messages together. And then you can put it into a verifier with the public key and say, yes, those 5 messages or 4 messages rather, were sent by the aircraft with that public key. So then you validated that set of messages. So that works in that sense. So the advantage of that is you have validation and it's scalable. So you can have a database somewhere of private and public keys, and then you can validate that all the aircraft are there. However, on the downside, you need a database of aircraft public and private keys, and you need to protect that. So that becomes a more infosec problem, and then you have all sorts of issues about revocation. What happens if someone pretends or steals an aircraft private key? Can you revoke that across all of the databases in the world, and that sort of fun stuff. But another upside is you could just have this whole side as a separate box, basically, rather than doing anything to the ADSB receiver. So you have a crypto bolt-on, basically, that signs everything and transmits it. So again, there's ups and downs to all of the different sides of it, but it's managing that risk and doing that. An improvement over the symmetric authentication as well is that it's only 7 messages for every 4 messages. So it's not a 75% reduction, it's a 58% reduction. But still, if you said to Heathrow, sorry, I know we said a quarter last time, you can fly 50% of your aircraft, that's better. That's still not going to cut it, really. So you need to find some sort of out-of-band channel to send that information down. So some other defenses that I didn't really do, but you could do, is you could do more sort of what active TCAS does, but better, because that's still pretty awful. You can do distance bounding protocols, where you send a message and then see what the delay is between the two, and to work out the range, and that gives you sort of a circle of range within which the aircraft could be, and then use that to validate whether the ADSB data is right. Some University of Cambridge guys did some work on this for ARFID. So we all do long-range ARFID attacks and that sort of stuff, so sniffing badges or replaying it over a long distance. So using distance bounding, you could work out whether that badge is actually anywhere near the reader and whether it should talk to it or not, which is quite interesting. But it does need a completely new radio and a completely new transmission system and all of this, and inordinate amounts of money. Another small change that you could do is a policy change. So at the moment, the FAA's response to ADSB injection is it's fine. We accept that because the ground station, we have lots of ground stations, so we can triangulate where the transmitter is and say that it's not where it says it is. And you're sitting there going, okay, so that's fine. So the air traffic control can tell where the aircraft is. But the aircraft in the air has one antenna. So it can't tell whether that aircraft is where it says it is. It just knows that something's talking to it. And maybe if you had a directional antenna, you could tell what the bearing is, but still, if you have the bearing, it doesn't matter where along you are, you could be right up in front of it. So that's not really a great defense. So making just a simple policy change to the way TCAS works is you could say air traffic control has a special code word or something that if they say this code word, then the resolution advisory doesn't apply anymore. It's false. We know it's false, and we'll tell you that. Because at the moment, there's no way for air traffic control to tell them that that RA is malicious because of the way the RA system is set up. However, and we have another downside here, as soon as you start telling pilots that they can ignore resolution advisories, more pilots are going to ignore resolution advisories and crash into other planes. So there is an enormous amount at the moment. You do a lot of research about pilots who, in fact, if you watch air crash investigation, most of the time it's the pilot has ignored the bleeping bit of hardware that says there's an aircraft coming and just goes, no, that must be wrong, and just plows straight on into it. I mean, go away and look it up. Go away and look at air crash investigation. Most of the accidents will be the pilot plowing it into something rather than the computer doing something wrong. So again, when you tell pilots, oh, it's fine, you can just ignore resolution advisories, you open up a whole new can of worms in pilot training, which isn't necessarily where you want to go. But if it's the only thing that stops people ejecting stuff, then you might want to do that. So as with all research, there are some caveats, and there's some places you go further with it and some future work. So the first caveat is this isn't actually a real aircraft, because our budget didn't stretch to getting a real aircraft. This is just a simulator, and I've done what I've done in a simulator. So any extrapolation of that to an actual aircraft, you have to take it with a pinch of salt, because it's not an actual aircraft, it's software running on my laptop. So the exact ADSB interface with TCAS might not do a resolution advisory, it might just display it as traffic, but without having an aircraft, you can't really tell, which is unfortunate. However, and I have some caveats to my caveats, active TCAS doesn't have any security either. There's no encryption or authentication on that. And that's a whole new category that you can play around with injecting into. If you clouded a TCAS display with non-threatening traffic, you're still increasing the pilot workload. And the pilot has to do a lot of things on an airliner as his normal job. So if you distract him away from that, you raise the risk of there being an incident. And in the aviation industry, we're not very risk tolerant. We don't like risks, because a risk means that your multi-million-pound aircraft with hundreds of people on board could go ploughing into a mountain, and that's not a great thing. So even if the likelihood of it is small, it's still a fairly major risk overall. And the next point that I want to bring onto is there have been people saying, oh, you can't do it, TCAS doesn't work that way. But in the future, they're bringing in something called ACAS X, which is the Automated Collision Avoidance System X, because the FAA is like that, aren't they? And this is part of that whole next generation. So the improvement on this system, where my attack might not work, is that my attack is guaranteed to work, because the only input to the system for this particular branch of ACAS will be ADSB. So this is a new system where you take just ADSB data and you bring it in, and then you do collision avoidance based purely on that. That is the reaction I had. But yeah, so if you want to go and read up on that, you can copy that later, or I'll try and tweet and put this presentations out. But they're bringing in this new next-gen system, and they want all of this stuff with no security, no authentication, nothing on it. So in conclusion, ADSB is flawed, it's legacy. It was legacy when it was invented in 2008 because it had nothing, and now it's next generation, apparently. Anyone can listen into traffic, so there's that whole can of worms that we haven't opened. Ground stations can filter out ghost aircraft, but the aircraft themselves, which are, remember, the important bit in this equation, can't do any of that. Anyone can pretend to be in a collision, and the aircraft itself will believe them, regardless of what air traffic control says. So you have mitigations, but they either reduce the bandwidth, or they have other knock-on effects, or there's a whole other can of worms associated with them. So really, you need this, it's the truism of information security. You need to combine technical and a policy situation. So you need to get the managers and the FAA to sit down with the techie people and go, right, let's hash out a way of dealing with this so that we don't make this mistake in the future when we go to things like ACAS X and all this sort of fun stuff. So I'd like to leave you on one final note. This is a laptop on eBay. You can buy a laptop really, really cheaply. Everyone knows how cheap laptops are. HackRFs, they're around $300 at the moment. So if we make a conservative estimate, that's about $301 to cause massive disruption and flight safety risk at Heathrow or JFK or any of these places. And that's with zero attribution as well. So there's no one can work out where you are. You can put a Raspberry Pi with a HackRF and dump it next to an airport and cause a huge amount of damage. On the eve of the attacks in America, Al-Qaeda was running a $30 million annual budget, according to the CIA. So when you sit and imagine how many of these systems they can put together, it doesn't take a large amount of imagination to see where that could go. Thank you very much. That's been my talk. If there are any questions, I'd be happy to take them.